We're welcoming a new generation of ground-based telescopes this week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. This week, we're exploring the upcoming Giant Magellan Telescope. I speak with Rebecca Bernstein, Chief Scientist for the Giant Magellan Telescope Organization, about how this cutting-edge observatory could revolutionize our ability to study the universe around us and the search for life beyond Earth. Then Casey Dreier, our Chief of Space Policy, returns to discuss his new op-ed in Space News. He'll give us an update on the White House's Mars plans and why political sustainability may matter more than rocket science in this case. And as always, we'll close out the show with Bruce Betts, our Chief Scientist, for What's Up. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Before we get into our discussion of the upcoming Giant Magellan Telescope, I want to send a huge congratulations to the team at the Vera C. Rubin Observatory. Just a few days ago, the observatory released its first images. And I tell you, they are nothing short of breathtaking. Rubin is just beginning its 10-year legacy survey of space and time. And fittingly, it's located in Chile, not far from where the Giant Magellan Telescope is being built. I'll leave a link to those images from the Rubin telescope on the page for this episode of Planetary Radio. You can find that at planetary.org/radio. And really, though, you're going to want to check these out. They are gorgeous. But our main topic for today is the Giant Magellan Telescope, or GMT. It's part of the United States' extremely large telescope program, which originally aimed to provide astronomers access to both the northern and southern skies through two powerful observatories: the Giant Magellan Telescope in Chile and the 30-meter telescope, or TMT, which was originally planned for Mauna Kea in Hawaii. But that vision is changing. The National Science Foundation announced that it will move forward with the Giant Magellan Telescope, but may not fund the 30-meter telescope's advancement to its final design phase. That decision comes amid major budget cuts and long-standing challenges around TMT's construction, which have faced deep and ongoing opposition from Native Hawaiian communities and broader cultural concerns tied to the stewardship of Mauna Kea. While TMT's future remains uncertain, GMT is now advancing into its major facility's final design phase, one of the last milestones before it becomes eligible for federal construction funding. The Giant Magellan Telescope is one of the most ambitious ground-based astronomy projects ever undertaken. It's the work of the Giant Magellan Telescope Organization Corporation, a nonprofit and international research consortium that's also headquartered near our office in the City of Astronomy, Pasadena, California. The construction of the telescope is already 40% complete, and major components are in development across 36 U.S. states. The observatory itself is being assembled at Las Campanas Observatory in Chile, which is an ideal site that offers direct views of the southern sky, including the heart of our galaxy. My guest today is Dr. Rebecca Bernstein, the Chief Scientist for the Giant Magellan Telescope Organization, and an astronomer at the Carnegie Institute for Science, one of the founding institutions behind this international effort. We spoke about the telescope's revolutionary technology and how it will work in synergy with other major observatories to open up a new era of cosmic discovery. Hi, Rebecca.
Hi, good to be with you today.
Thanks for joining me. I have a background in astrophysics, although I speak primarily about planetary science these days. And I am so excited for the Giant Magellan Telescope to finally come online. Can you start by sharing, personally your vision for the GMT and why you've dedicated so much of your career to this project?
Well, I think a really good starting place for thinking about the excitement of the whole telescope is the example of exoplanet science. So, as recently as 30 years ago, we really didn't know very much about planets beyond our solar system at all. We had theories about how planets form and evolve, but we really didn't have any proof that there was even a single planet beyond our solar system around another star. And we've really done an amazing job of understanding those planetary systems in the sense of just cataloging what is out there, starting to get a sense of what the basic statistics of those planets are. But if we want to really understand how planets like our own solar system come to be, we need to be able to study the individual planets in much more detail. And to do that, we really need better tools. And it basically all comes down to the resolution that you can get with the telescope, because planets are very faint and they're next to very bright objects, and you need to separate those two. It's almost a really good analogy. It's like trying to observe a firefly next to a searchlight. So you need resolution to separate the very faint planet from its parent star. You need very sophisticated instruments to block out the light of the parent star. And then you need to be able to take spectra. And spectra let us measure the dynamics of a system. Those dynamics can give us masses. The spectra also tell us about the chemistry, the composition. And that, when we're talking about the composition of an atmosphere, that starts to tell us whether planets might have life and whether they're capable of hosting life and whether they in fact do host life. So it really would open up our understanding of what's out there, and ultimately whether we're alone, whether there's not just the potential for habitability, but whether we can actually find evidence that there is life on another planet. So GMT really has some very unique design attributes and capabilities, and some of them are spectacular for exoplanet science. So, for example, we're building very high-resolution spectrographs, which are exactly what's needed to study the planets in detail. One of those instruments is being built at UT, University of Texas at Austin. Another very unique instrument is one that is what we call an extreme adaptive optics imager that also is a coronagraph. The name is GMAG-AOX, sort of mashing up all of those concepts in one. That's being built at University of Arizona. And that instrument, coupled with the Giant Magellan Telescope, really will have completely unique ability to access cool, faint planets, which is exactly what you need to be able to do in order to understand how planets like our Earth came to be, and in fact, how the whole solar system formed. So GMT is really an exceptional tool for the future study of exoplanets, and it's just one example of the kind of way that GMT is going to just break open the future of astronomy and what we can really learn about our universe.
Our listeners have heard me say this before, but when I was in undergrad, I did my research looking for exoplanets. And that was not that long ago, but it was just a little bit before the Kepler Space Telescope launched. And at the time, we literally had to do it one star, one transit at a time. And now we're at this phase where just the universe is opened up to us. But because of our limited technology and what we're allowed to actually see out there, we're finding a lot of large planets, a lot of really cool places. But if we want to find a place like Earth, we're going to need a telescope like this. But when I present this to people, people will ask me something like, well, we have instruments like JWST in space, right? What are the limitations of those kinds of space-based telescopes? And why do we need something like an extremely large telescope here on Earth in order to accomplish that kind of science?
When it comes to studying exoplanets, the first thing you need is resolution. And to get to those extreme resolutions, you need a very large telescope, and you need it paired with a very effective instrument. So as I was saying, the next generation of telescopes, the ELTs, are really going to crack open that access to resolving planets from their parent stars in a way that will be dramatically better than what you can do with JWST. So JWST is a 6.5 meter telescope in space. But when you are talking about the diffraction limit of a telescope, the limiting resolution that can get, it gets better with the diameter of the telescope. So the larger telescopes can be built on the ground, the next generation, these ELTs. And GMT in particular has not just that larger diameter, but the ability to pair that larger diameter with the ideal instrument. The instrument I was mentioning, GMAG-AOX, will actually be able to get to much higher resolutions than any of the other two ELTs that are even being designed today, because it can also go to shorter wavelengths. So resolution is a combination of the diameter of the telescope and the wavelength of the observation. Being able to go to shorter wavelengths gets you to those even better resolutions. proportionate with the wavelength of the light. But also, there's another really key point, which is that if you want to understand how all planets form, if you really want to understand how you end up with a planet that can host life, a system like our solar system, you can't just study the hot, young planets. You need to be able to reach the cool planets that have had time to evolve and develop life and are at those more temperate temperatures so that they can have liquid water without being too hot to host life and without just having that water freeze out. So it's that perfect temperature, older planets and rocky planets, smaller planets around solar type stars. That is the sweet spot of what we're looking for. And the Giant Magellan Telescope is really going to be unique in its ability to access that regime, the cooler, older planets closer into their parent star, rocky planets around solar type stars, and GMAG-AOX is the instrument that's going to be able to do it. So we will be able to take spectra of those planets, and that is something that right now JWST can't get anywhere close to doing.
Yeah, and to be clear, I mean, JWST can look at the spectra of atmospheres on worlds by seeing the light of the stars actually passing through that atmosphere and trying to deduce what's inside them. But this telescope is trying to do, I mean, not just that, but something a little different, actually looking at the reflected light of the star off of these worlds. That is just a whole new level of science that we haven't even begun to crack open yet.
That's right. You said the magic phrase. We're looking at the reflected light of the parent star off of these planets. And that's the way we look at the moon, right? We see it in the reflection. We see the light from the sun reflected off it. When you look back at the Earth from space or from the moon, you see it reflecting the light of the sun, of its parent star. That's exactly what you need to be able to do in order to study cooler, potentially habitable planets. And you can't do that unless you're looking at optical wavelengths. And again, GMT and GMAG-AOX will do that.
Yeah, some other telescopes do have this kind of, coronagraph technology, but like, how would you compare what we'll be able to resolve with this telescope when it's finished with the actual direct images that we've gotten so far? Because we have seen some worlds, but, not very clearly.
Yeah, so we've made gorgeous observations of larger, hotter planets at larger separations from their parent star than will be our eventual goal if we want to study Earth-like planets. And the kinds of data we'll get are very similar. In addition to being just able to access the cooler, closer in rocky planets, we'll be able to get spectra of them. Now, once you're getting spectra at optical wavelengths, you can really look for the right combinations of molecules that let you distinguish geophysical origins for where those gases and molecules and elements come from biological origins for those gases and molecules come from. And that really lets you crack open the problem of whether you're seeing signs of life or not.
You said a little bit about this earlier, but what wavelengths are we going to be capturing with this telescope that's going to allow us to do this kind of, spectral observation?
Right. So the Giant Magellan Telescope works from the UV cutoff at the blue end of the optical spectrum, gets the entire optical spectrum, and then into the near infrared and mid infrared. So it really covers that entire bandpass. We have optical high resolution spectrographs. We have near infrared high resolution spectrographs. That extreme AO imager, GMAG-AOX, will work into the optical, which is really spectacular. Some instruments do that now, but actually GMAG-AOX has a little sister called MAG-AOX. It exists now in Chile at the same observatory at the Magellan telescopes. And it is really a pathfinder for this. And it demonstrates the whole technology and technique.
This is going to be a really large mirror, but we can't actually manufacture a mirror on that scale. It's actually, you have to build it out of smaller segments. And even then, we're pushing the limits on how big we can manufacture a mirror. What are the things that limit our ability to create mirrors of this size? And how many and on what scale are you going to be using for this telescope?
So the Giant Magellan Telescope is made of 7 8.4 meter primary mirror segments. They are the largest segments the largest mirrors that can be made anywhere on the planet, and they're actually made at the University of Arizona's Mirror Lab. The Mirror Lab has made 8-meter mirrors before. The Keras Mirror Lab has made 8-meter mirrors, a little over 8, I think it's 8.2-meter mirrors before. But what's so spectacular about the mirrors for the Giant Magellan Telescope is how strongly curved they are. That lets them bring light to a focus in a very short focal distance. So it lets them be very strong. That lets us make a very compact focal plane. And that doesn't sound like it's going to be so important, but it makes us be able to see a huge angle of the sky without having to build gigantic instruments. And that is just another really spectacular thing about this telescope. It lets us access large areas of sky with compact instruments. Compact instruments are faster to build, they are lower risk, they can use a wider variety of optical materials that are actually higher performance. It's just a win-win-win-win-win. And so it really does boost the overall performance of GMT while keeping the costs down. And that ability to see a very large area of the sky is one of the things that's very valuable for cosmology and for studying galaxy evolution. And it is one of the reasons why GMT is the perfect telescope for following up the observations and the survey of, for example, the Rubin Observatory and the LSST survey that it's doing. So that survey is taking place, that observatory, the Rubin Observatory, is in Chile, it's our neighbor. It's just a few summits south of where Las Campanas Observatory and the Giant Magellan Telescope will be. And it's going to survey the whole sky, every few nights to find changing objects. And those are essentially exploding stars that are interesting both because of their physics and because of the cosmology that we can do with those basically signposts in the universe. It'll also have a huge galaxy catalog, and so we'll be able to study galaxy evolution just from the objects that are in their data alone. But these explosions that the survey is really designed to find, we don't get the full science out of those discoveries unless you can follow them up. So the Giant Magellan Telescope will be able to take spectra over huge areas of the sky very efficiently in single exposures. So you get a large number of objects in single exposures. And that is really because of the unique design of the Giant Magellan Telescope. So GMT will be spectacular both for exoplanets, for cosmology. It's really just got an enormous breadth of capabilities because of its design.
Yeah, when we combine that with the capabilities of other telescopes, especially knowing that we've got these space-based telescopes that are honing in on very small regions of space, and then combining that with all the other telescope surveys with this ability to resolve things at this level, the things we could learn are just absolutely mind-blowing, even just beyond, the exoplanets and seeing, the deaths of stars. And, there are some implications for learning more about the history of the universe itself and how cosmology falls out over time.
Absolutely. And the other really amazing thing is that by building in Chile, we have the best location in the world for actually doing this science from the ground. So there's really almost 70, by the time GMT is built, almost 70% of the astronomical facilities on the planet will be in Chile. The US will have well over $2 billion worth of astronomical facilities in Chile. And we're really part of a decades-long strategy for developing a set of facilities that can really do just groundbreaking science in the best location on the planet for observing the sky. It's at the western edge of a continent. It's at high altitude in the Andes Mountains. It's in a desert. All of those things together give you smooth, calm air after the air has moved from west to east over the ocean. So it doesn't get choppy moving over land. So that's why the west coast of a continent is important. By being in a mountain range or above a lot of the atmosphere, that's also very important for being able to detect more photons and more accurately. And then, of course, you don't want to be looking through clouds. So being in a desert is spectacular. And if you just think in your mind about what other places there are on the globe that give you that combination of attributes. The west coast of the United States used to be pretty good, but we don't have as high mountain ranges, and now all of those mountain ranges are near cities. The west coast of Africa, that's where the Canary Islands are, but they get slightly affected by the dust from coming off the continent, the Sahara Desert, and they're not quite as high. They're a little more humid. It's really a spectacular location for science. And the United States has long recognized that. We have a huge history of building facilities for astronomy in Chile. And we have a wonderful relationship with Chile. Chile puts enormous value on science. It's a real social and psychological investment that they have in science and technology. They have dark skies protection legally. Their federal government protects the dark skies. We own land there. Our partnership owns land in Chile. It's almost like we operate like an embassy. In fact, we have a special relationship with the government. It's really a very, again, a win-win. I keep using that phrase, but it's a very positive relationship on just a number of levels.
Yeah, there aren't a whole lot of downsides for having telescopes in that area, but I will say that Chile is pretty frequently affected by large-scale earthquakes and that kind of thing. How is this telescope equipped to deal with that kind of situation?
It is definitely a seismically active area, but you know what? Almost all mountain ranges are. That's how they become mountain ranges, right?
Truth.
If you're lucky, if you're not also on a volcano.
That's so true.
So we do have seismic isolation system underneath the telescope. And it's interestingly, it's a very similar strategy and technology to the system that is underneath City Hall here in Pasadena. So basically the idea is that the telescope this is very simplistic, but just to give you a sense of how it works, the telescope is essentially on roller skates. And those roller skates are sitting inside of large, like giant salad bowls. So the skate can settle to the bottom of the bowl, and the telescope can ride safely on that skate while the Earth moves underneath. So that's the idea.
Do you have seismographs and stuff up there at the observatory as well?
You know, I don't think we do, but we're plugged into systems in Chile that will give us early warnings.
Mm-hmm. Yeah, I've worked at some observatories across California, which of course has many earthquakes. And one of my favorite things, because inevitably you end up with an earthquake, is immediately taking the whole crew down to go look at that seismic tracing anytime it happens.
It's whenever you're in a seismically active area, it's a big deal. So we do have an award-winning design that we're utilizing, and it's really the first class of telescope. There are a lot of telescopes in Chile already. This is the first class of generation telescopes that will be built with active seismic isolation involved. So we do intend to keep the telescope safe.
I mean, the technology being used on this thing is clearly absolutely revolutionary, which is part of why it was named as one of the highest top priorities in the National Academy's 2020 Decadal Survey for Astronomy and Astrophysics. What does it mean to you that this project is held at that like high level of esteem among the scientific community?
Well, it's a huge honor, and we worked hard to help the community understand and envision the science that they would do with this telescope. And I think now the whole community is invested, as Astro 2020 stated very clearly. It is a top priority of the entire community. It is well appreciated by the entire community that this telescope will be able to address the key questions for the next decade and beyond. And that's really one of the amazing things about ground-based telescopes. They can be continuously updated for decade after decade after decade with state-of-the-art instruments. You know, when you buy a new cell phone, often what you're buying is the new camera. And the new camera is better partly because of the new kinds of detectors, the new sensitivity of the detectors, the new optical systems in there. And that kind of thing we can constantly be updating on the telescope. So we built these telescopes to work for 50 years. The Giant Magellan Telescope is a partnership that will be public-private. So we're bringing an enormous, leveraged good deal to U.S. taxpayers. So the combination of benefits from a ground-based telescope that's partly private, partly public, and is such an efficient designed for science is really, it's going to revolutionize astronomy for decades to come. And the total cost is less than about a fifth of one JWST. So it is a spectacular deal, even before you consider the leveraging of the funding.
It's actually quite lucky to be able to just swap out instruments if anything breaks, anything like that. We don't have to launch people into space. And even if we wanted to with JWST, that thing is so far out there, we wouldn't be able to do it if we wanted to. How far along is this project in its actual construction at this point?
We are actually over 40% in construction. So at the site, we have already done the hard rock excavation. So we're ready to pour concrete. We have a lot of the infrastructure all prepared at the site for doing that, for pouring concrete and moving straight into the full construction. But you don't want to start doing the next steps at the site until you're ready to just crank all the way through. You don't want to lay the concrete foundation and then wait years before you take the next step. So you want to wait until you want to wait at the stage we're currently at, having done the hard rock excavation, having prepared the site. Now what we're focusing on is building the components. We're building the instruments. You've already mentioned the mirrors. We have 3 mirrors completely finished. All 7 of them have been cast. The next ones are being polished. We are making the secondary mirrors that reflect the light, that actually do our adaptive optics correction and send the light to the instruments. We're doing all aspects of the construction in sensible order so that we'll be prepared to then reassemble the telescope in Chile. And all of that I just mentioned is being done at our partners around the country, at some of our vendors around the world. The telescope is being made in Illinois at Ingersoll Machine Tools. We mentioned the mirrors already. Instruments are being made University of Arizona, UT Austin, other partners around the country, and our other international partners as well. So it's just, we are moving forward on everything.
We'll be right back with the rest of my interview with Rebecca Bernstein after the short break.
Greetings, planetary defenders. Bill Nye here. At the Planetary Society, we work to prevent the Earth from getting hit with an asteroid or comet. Such an impact would have devastating effects, but we can keep it from happening.
The Planetary Society supports near-Earth object research through our Shoemaker NEO grants. These grants provide funding for astronomers around the world to upgrade their observational facilities. Right now, there are astronomers out there finding, tracking, and characterizing potentially dangerous asteroids. Our grant winners really make a difference by providing lots of observations of the asteroid so we can figure out if it's going to hit Earth.
Asteroids big enough to destroy entire cities still go completely undetected, which is why the work that these astronomers are doing is so critical. Your support could directly prevent us from getting hit with an asteroid. Right now, your gift in support of our grant program will be matched dollar for dollar, up to $25,000. With your support, working together, we can save the world. Thank you.
Yeah, it takes a lot of people and a lot of institutions to put something together like this, and a lot of time and a lot of love. And you guys are doing. You guys are doing.
We actually have construction going on in 36 states.
Wow,
it's pretty amazing.
Yeah, I mean, we've been talking a lot recently about how these kinds of projects touch so many different states and districts across the United States. And that's part of why space exploration is so wonderful. It's about bringing together communities across various places around the world to accomplish something absolutely mind-blowing. And when this thing is done, my gosh.
Yeah. I mean, when we were visiting Ingersoll to see the progress on the telescope mount itself last summer, we were talking to folks who had engineering degrees, who were expecting they'd have to go away to use those degrees. And they were thrilled to discover that they were going to be able to stay, near home and work at Ingersoll to develop, this telescope and do something so technologically fascinating and not have to move away from home. It really, being able to do this at different locations in the United States is really, again, it's a really nice illustration of the integration of technology and innovation with science. And it's a huge part of U.S. leadership and maintaining U.S. leadership in those fields.
Yeah, we're going to need to take that next step, unfortunately. Launching things into space is really difficult. You got to origami that telescope into a tiny little rocket in order to make things work.
That's right.
You know, making telescopes of this size is really complex. And in this situation, you've not only created some of the largest mirrors that humanity has ever built, but you've also built in these kinds of adaptive optics systems. Could you walk us through how adaptive optics kind of works traditionally and why the deformable mirrors is like a next step in that technology?
I'd love to. Let's talk about the adaptive optics. Let me just start by talking for just a minute about what we can actually launch. So we have 6.5-meter telescopes in space. Obviously, JWST is a perfect example of that. To put larger telescopes in space is actually quite difficult. It's not, you don't get around the problem just by making the mirrors segmented. Building the structure itself is also something that you need to prototype. You need to take small steps in order to guarantee success. You can't just go from a 6.5-meter all the way to a 15-meter. So even in space, it's a process of learning to build the next thing. And even in space, you need adaptive optics to control the mirrors accurately enough and to do the coronagraphic corrections to get the kinds of observations that we're talking about. So actually doing this on the ground is the best way to achieve these resolutions in these very large collecting areas. Okay, so now let's talk about adaptive optics. So the idea here is that when light comes through the atmosphere, and in the case of a ground-based telescope, you can think of the light as being a wave front, a sheet of light coming down through the atmosphere. And as that light is traveling through the different thermal pockets in the atmosphere, it gets ripply. And in order to get to the sharpest resolutions we can, we need to make that light flat. We need to unbend the ripples and take out the turbulence, take out the ripples that are caused by the turbulence in the atmosphere. So basically, adaptive optics, the whole idea of adaptive optics is to remove the effect of turbulence in the atmosphere. And you do that by having mirrors that can actually change their shape thousands of times a second on scales of centimeters across the full mirror, so that when light reflects off of that mirror, the rippling effect is completely removed. So you reflect light off of a mirror that can change its shape, and when the reflected light bounces off, the effect of the turbulence is gone. So we do that turbulence removal step. We do the adaptive optics step with our secondary mirrors, which means that by the time the light gets to the instruments that can reformat and record the light for scientific measurements, the light is already corrected. So light comes down to the primary mirror, gets reflected up to the secondary mirror. That secondary mirror does the turbulence removal, does the image correction, and then it gets sent down to the instruments where they record the light. So our adaptive optics system is what we call prefocal. It happens before the focus of the telescope. That's critical because we're not wasting any reflections. We don't have to build in any extra reflections, any extra instruments, and we can correct all the light at any wavelength at any time to get rid of the turbulence in the atmosphere. That makes it a profoundly powerful telescope. We can do what's called ground layer adaptive optics, where we remove a little bit of the turbulence or half the turbulence, say, over large areas of the sky and wide fields of view, or we can get perfect turbulence removal over very small areas of the sky to look at individual objects like planets. And by having that prefocal system, it's efficient and it gives us all the options for when we use it and what wavelength of light we're looking at. It's very exciting to have a telescope where this adaptive optics capability is built in from the beginning.
In order to do this kind of thing, you're going to need some really flat mirrors. Like, to what level are these things polished?
Yeah, so the mirrors are accurate to better than 1/1000th of a human hair. And that's each mirror individually. When you put them then together, all 7 of our primary mirrors act like a single surface that has that accuracy. Yeah, so it is really a spectacular feat.
You've highlighted a few of the instruments on board this thing, but are there any other ones that you're particularly excited about?
I'm I'm excited about all of them. So we have instruments that can access that very wide field of view. One of those is called GMAG-AOX. It's a spectrograph that's a lot like spectrographs on the telescopes that we are familiar with today, but this one is just much larger and much more capable, and will deliver, again, a large wavelength, and that large field of view lets us do many, many objects at once. And if you think about how powerful it is to have a wide field of view, if the science you're trying to do requires that you observe, say, 100 galaxies, but your field of view is such that you can only get 30 galaxies at one time, then you have to observe in 3 times. By having a wide field of view and being able to observe 100 objects at one time, you've just essentially given yourself 3 telescopes. That's the power of having the capabilities and the instrument pairing with the telescope that I'm describing. It really just leverages the amount of science you can do instantly. So we've got those wide field of view instruments. Another one is called Manifest. It's being made by our partners in Australia. We have 2 very high resolution spectrographs, one working at optical wavelengths, the other working at infrared wavelengths. Those are being made at Harvard and the University of Texas at Austin. And then we've got instruments being made in Arizona, University of Arizona as well. And when I identify those are the lead institutions. There are partnerships around that involve other members of our partnership that are contributing to those instruments.
So a lot of what we're interested here at the Planetary Society is about learning about the worlds around us. And doing this kind of thing is necessarily going to take some really complicated spectroscopy. What kind of elements and compounds are we going to be looking for in these atmospheres? And why is this telescope so uniquely suited to doing this kind of science?
Exoplanet science is a very young field, and we know some of the key features that we might find in the atmospheres of other planets that will help us understand what processes are going on those planets, be they biological or geological, or whether the planets contain water, et cetera, et cetera. We're constantly learning better how to actually make the observations. And we're also constantly learning what combinations of things we're going to have to look for and detect in order to be confident that we're not claiming a false positive detection of life or a false positive detection even of a particular molecule. So it's a really young science, and it, even in the time I've been paying a lot of attention, even in 5 to 10 year timescales, every couple of years there's some really new awareness of how careful you need to be, or the best techniques to use, or there'll be some new discovery about how exactly you want to do the measurements. One of the things that makes exoplanet science so exciting right now is the rate at which it's evolving.
Yeah, I'm thinking particularly of a story that we've covered a couple times in the last year. It was the story of K2-18b and the detection of dimethyl sulfide there. I know there's a lot of skepticism around this result because of the weak signal, but I think this is one more reason why this kind of telescope is so useful, because if we make those detections of chemicals that could potentially be indicators of life, we're going to need to have some follow-up observations that are really serious, because even if we find something that would be a dead giveaway for life on Earth, making that kind of claim takes some extraordinary evidence, and we're going to need to do just a lot of science.
That's right. So it's not just that you want to verify the measurement, which you do. Ideally, you want the same measurement to be made with multiple telescopes and multiple instruments, because you never know what kind of systematic effects might have influenced the data that you collect. But in addition to that, you want multiple ways. You really want to check your interpretation, because even if you're confident of exactly the feature you've detected, you want to be sure of the implications, how that feature might have been formed, or how that gas or molecule might have been formed. And these are, as you're saying, extremely subtle. They require enormous accuracy, and the extraordinary claims, as they say, require extraordinary evidence. So,
Yeah. But GMT isn't working in isolation, obviously. It's designed to work synergistically with other major telescopes, primarily things that are down looking at the southern sky. You mentioned the Vera Rubin Observatory, but are there any other major observatories that you're excited to work with in the future?
Absolutely. So there are a number of telescopes in Chile. ALMA is the radio telescope. It's particularly powerful for understanding star and planet formation. It's also very powerful for galaxy evolution. And there are, of course, the European ELT will be in Chile. And I think the thing that we were just mentioning about the need for multiple observations, even of exactly the same thing, I think that cannot be overstated. So I think that's very powerful. Even GMT and the European ELT will have very different capabilities. The European ELT is much more geared towards the infrared and what doesn't have nearly as wide a field of view. For a while, it won't have as high resolution for exoplanet science at optical wavelengths and those cooler planets. So there's really an enormous range of complementarity. So I think that's going to be very exciting. The telescopes in the South Pole do for microwave background radiation. They often observe high redshift galaxy clusters that the Giant Magellan Telescope will be very powerful for complementary observations there. We need a telescope in the US community the size of GMT in order to do follow-up of gravitational wave detections. LIGO has already demonstrated how powerful it is and the fast fading objects that it detects. You really need to get to find them, start taking spectra of them very quickly. A more sensitive telescope like the Giant Magellan Telescope is ideal for that. The list just goes on and on.
Yeah, especially with LIGO. I mean, I was absolutely mind blown during that incident where they had two neutron stars collide with each other. I think a lot of people, when they think about LIGO, think about things like black hole collisions. But when there is some kind of optical object that we can actually see, an explosion, you need people to get on that really, really fast. And through even just that one incident early on, we discovered that a lot of the elements we thought were created by supernovae actually come from these colliding neutron stars, and they are pivotal to, not just the creation of heavy elements, but life itself. We're going to need something like this.
That's exactly right. So as you just said, the neutron star collisions that form black holes are little chemical element factories. They make all of the heavy elements that cannot be made in the centers of stars, and they are predominantly responsible for those heavier elements. So the only way we know that is because very shortly after LIGO detected that event, very quickly, telescopes, in fact, at Las Campanas, found the galaxy where that collision took place, where those two neutron stars were located and had collided, and then took the follow-up spectra to figure out what happened during the formation of the black hole, that all those chemical elements were produced, and watched the physical processes that led to the formation of a black hole. So it was extremely exciting. And with the Giant Magellan Telescope, we'll be able to detect exactly those kinds of sources farther out, which gives us access to many more of them. We'll be able to make the observations much more accurately. We'll be able to use them, in fact, for cosmology and other cool tricks that are accessible when you can make highly accurate observations. So it'll be very exciting.
I think when the telescope comes online, it's going to be really special. And we're going to end up with a whole new generation of people that, looking at those images, are then inspired to go into science themselves, or maybe even support these projects in the future.
I just could not agree with you more. I think that we saw that with the first image release from the James Webb Space Telescope. NASA could barely get those images out fast enough before they were on over 150 newspapers on the front page, above the fold, as we say. The very next day, they were reposted in over 1 billion social media posts within the next week. And they practically seem like science fiction, even to scientists. We can only guess how many kids saw those images that day and decided they wanted to be scientists. So, I think astronomy has a really unique ability to reach the imagination and curiosity. And people who, aren't even scientists, right, don't consider themselves scientists yet, but may consider themselves scientists in the future. And it's also, I think, just a really good illustration of the fact that the universe is, for all of us, the ultimate physics lab. It creates for us experiments. It shows us things, particularly at the very highest densities and the very lowest densities, the very highest energies, that we cannot, it sets up experiments we cannot set up on the ground. We cannot create in physics laboratories here. And it's available to everyone. All we need is big telescopes to watch it.
Well, last question then. When do you hope to see first light from this telescope?
Early 2030s. We are looking forward to getting this telescope on sky in the next decade.
Well, I know I'll be sharing those images on social media the moment it happens.
There you go.
Well, thanks so much for taking the time to talk with us, Rebecca, and good luck with building this thing. I know there's a lot left to do, but honestly, it is worth every single moment of love and effort going into this. I cannot wait to see it.
Well, it is a labor of love, and it is my pleasure to talk to you. Thanks very much for your time.
While the Giant Magellan Telescope just cleared a major hurdle on the path to federal support, the broader outlook for space science funding is far less optimistic in the United States. The White House's proposed 2026 budget for NASA includes the most sweeping cuts to science in the agency's history, slashing nearly half of its science funding, canceling major missions, and shifting human spaceflight priorities away from the moon and toward Mars. Casey Dreier, our chief of space policy at the Planetary Society, recently wrote an op-ed for Space News called "The Administration's Anti-Consensus Mars Plan Will Fail." It warns that this new Mars initiative is built on shaky ground. I spoke with him to learn why this dramatic shift in direction may undermine the very goals it hopes to achieve. Hey, Casey. Thanks for joining me.
Anytime, Sarah. Nice to be back on the weekly show.
So you open your piece with this powerful statement: this Mars plan is going to fail. And that's a pretty bold claim. What makes you so certain that this proposal is politically unsustainable, even if the technical goals are sound?
Everything is downstream of politics. The idea is basically, it's straightforward. Actually, it sounds like a bold claim. I'm actually, again, he's pretty confident about this, unfortunately, which is, the idea is, orbital mechanics don't work on electoral timescales. They are very inconvenient in that sense, particularly in the United States. And right now, there are two opportunities to launch to Mars, 2026 and 2028 in this current administration. At some point, the next opportunity will be under a different president. And that means that they have to continue moving through, or at least committing to, the foundation set right now. And unless you do the work to make sure that there is someone there to pick up the baton and carry it forward, your program will fail. And it has failed, particularly in human spaceflight. These efforts to go back to the moon and go to Mars have failed at literally every single opportunity since the end of the Apollo program, except for Artemis from the first Trump administration to Biden. And that was not by accident. That was a very deliberate effort. And they're basically dynamiting this coalition that enabled this to continue, making it politically unviable if a Democrat is in power in the next presidential administration, or even a Republican coming in without a broad set of national interests that it serves. If they just don't care about Mars the way that President Trump does, it will also fail. And so you just don't have enough time to build up a huge program in the next 3.5 years. Particularly, again, we just saw Starship blowing up on the pad the other day. And so we are very far from this launch opportunity from working out.
You write that Mars deserves better than being associated with the destruction of science and international cooperation. What kind of Mars effort do you think would be worthy of support? And what would it take to build the kind of coalition needed to sustain it?
Coalitions are built by addition, not by subtraction. And this is sometimes at odds with the ideal engineering outcome, right, of a project. which, there's a proper balance for it. But it doesn't matter if you have the most pristine, efficient engineering plan for sending people to Mars or the moon or whatever. If you need public funds to do it, if it's politically inviable, it is irrelevant. And we have seen examples. Artemis is a great example of bringing in international partners, commercial partners, existing large contractors, building a political base around the country, not just in NASA centers, and making it in a way that engages your political opponents, right? Space has been and deserves to be an opportunity to build unity in our country as opposed to division. And it has generally been used for unity in the past. There's no reason space has to be partisan. There's no reason it doesn't have to be either, right? That there's no firm foundation keeping it nonpartisan. It can float, particularly if one party or ideology really embraces parts of it. It can drive opposition against it by really kind of being associated with one party over another. So this is a real opportunity to step back and say, learn the lessons from your first administration. What else did Biden and Trump agree on policy-wise? But Biden took basically the first Trump administration's entire moon plan and continued it forward. That is a huge opportunity to build on. And that took a lot of, shoe leather going back and forth between Congress by Jim Bridenstine, by building and making an additive coalition of Artemis, increasing NASA's budget, not making Mars contingent on the destruction of something else. That's how you build a coalition.
I'm sure a lot of people are hearing this and thinking, well, we're going to Mars, and they want to feel excited about it.
I want it to work. I want humans to go to Mars in my lifetime too, right? We all do. And I think this is the point here, is that I'm even putting aside, let's say, if you're all for the cuts to science, if you're all for the cuts to the other parts of NASA, you do think that NASA needs to focus on just deep space exploration for humans. Even if that's the case, the way this program is being put forward and not defended, and that there's been zero effort to build a coalition, is that even that goal will also fail. Right. So it is destructive and self-sabotaging in the same vein, which means it's not good policy. So again, even if you want this to be true, and I do, but even if you accept all the destruction, it will fail. Right. And so let's make a policy that works and gets us to Mars, back to the moon. And, obviously from our perspective, does the other things, right? These really important, unique aspects of the space program. It can be done. There's no reason we have to make this a divisive area. We can make it this unifying area again. And this is what I want to emphasize, and this is why we shared this with the broader space community, is that this is, if nothing else, we should not pursue a self-negating space policy. We can do better.
Well, we'll keep following the story as it unfolds. Thanks again, Casey.
Anytime.
Now it's time for What's Up with Dr. Bruce Betts, our chief scientist at the Planetary Society. Hey, Bruce.
Hello, Sarah.
New telescopes. Let's go.
Oh, big new telescopes. Let's go, go, go.
But in order to build this Giant Magellan Telescope, you need funding. And clearly we're in a moment in the history of science in the United States where funding is not as easy to come by, and a lot of things are being scaled back. And the original vision for this U.S. Extremely Large Telescope program was to have 2 of these next generation observatories. And one was going to be in the Northern Hemisphere and one was going to be in the Southern Hemisphere. And it looks like right now we're going to be getting funding just to build one of these 2 telescopes, obviously the GMT, not the TMT. But what is it that we could gain if we had one of these giant telescopes in both hemispheres?
First of all, full sky access. So you can only see half the sky. I mean, it's more complicated, but basically you're missing half of the stuff that you can see if you're only in one hemisphere, or at least a lot of stuff. There's that whole rotation and going revolution. But so that's the big thing you're missing. You're also missing more observing time, because it's going to be fiercely competed to get time on these large beasts like that. New discoveries. I mean, the fact that we won't be seeing things, both ones that are there all the time and then transient events as well, as faster, following up on a gravitational wave event or a supernova. You can get faster response times if you can both see it. You get richer data, more complicated data. You're also boosting international astronomy and having a more global effect. But first of all, it's just there's a lot you would miss. But anyway, more telescopes, big telescopes, more telescopes, big telescopes. Bruce likes them.
Really, so much of my conversation with Rebecca was about following up on other observatories internationally and making sure that all these telescopes are working together so that we can get multiple observations of the same thing.
Right.
And when most of the telescopes are in the Northern Hemisphere, it's a little challenging to follow up on their observations when your telescope is in Chile.
Yeah, no, that's something that comes up in different aspects of astronomy. So I've been living in the world of Shoemaker-Neo grants and looking for asteroids, and when you have fewer observations in the southern hemisphere, we're kind of blind, or at least don't have as good a wide-ranging surveys, or we didn't until new telescope just firing up down there. But still,
which one? Vera Rubin?
Vera Rubin, yeah, it's going to be huge for discovering objects, not only near-Earth objects, but throughout the solar system, presuming it does what it's designed for. And they're optimized for different things. So you get a Vera Rubin, which is actually pretty amazing because it gets good resolution and wide angle, but still you can't get super duper nifty resolution like you will with one of these monster telescopes like the GMT. Even from the very large Vera Rubin. So more telescopes, big telescopes, more telescopes, big telescope.
So say we all. Well, do we have a random space fact this week?
I debated, but yes, we do. We have a random space fact. Asteroids. So I found this out from some of our updates from our Shoemaker-Neo grant winners, which are appearing on our website. When this goes to air, you can find out what they've been doing. Amazing amateurs doing the equivalent of professional observations and follow-up and characterization. And one of the things that Luca Buzzi and the group at the Schiaparelli Observatory in Italy observed was an impactor. Actually, they observed two of the impactors where asteroids were found a few hours before they hit Earth. And we're getting to the random space fact, which is that their observations of 2024 BX1, which was about a 1 meter asteroid, so very small, burns up in the atmosphere, looks spectacular, fastest spinning asteroid, at least at the time, and this wasn't very long ago, 2.59 second rotation rate. So spun in about 2.5 seconds as it was coming in. And you can only get that fast with a nice small object, but still I thought that was quite an image to picture it spinning as it came in and hitting Earth. And as you have a whole variety of spin rates of asteroids, including the much larger ones, which tend to be many hours in those cases, sometimes weeks, and you have weird tumbling things instead of simple rotation. Smaller ones tend to, in a ice skater pulling their arms in kind of way, spin up, and you get some of these faster rates. But like so many other things, other than all looking pretty much like gray potatoes, everything else varies considerably in the asteroid population.
I like the ones that tumble all willy-nilly, but I'm a bit chaotic.
They hurt my brain. You're chaotic.
Also, happy upcoming Asteroid Day. I think that's on June 30th. So
it is indeed a time to remember the significance of defending the Earth from asteroids. In 1908, that was the day that the Tunguska event occurred, where a asteroid came in, airburst, and leveled 2,000 square kilometers of forest in Siberia. Fortunately, not where people lived at the time. So, hey, let's be careful out there and keep working towards defending the Earth from asteroids. All right, everybody go out there, look up in the night sky, and think about the fastest you've been spinning around. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with more space science and exploration. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review and a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email, planetaryradio@planetary.org. Or if you're a Planetary Society member, you can leave a comment in our Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members who love space-based and ground-based telescopes alike. You can join us as we work together to build a bright future for space science at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Casey Dreier is the chief of our monthly Space Policy Edition. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which was arranged and performed by Peter Schlosser. And until next week, Ad Astra.